Good morning, everyone. My name is Mike Hirpara of Computer Science Department. Have you ever wondered what happens when we press a button in an elevator and it smoothly moves to the desired floor, opens the door at the right moment, and safely handles multiple requests? Behind the simple actions lies an intelligent digital control system. Today, I'm going to present how sequential circuits, one of the most important concepts in digital electronics, are used to design an elevator control system. This project demonstrates how memory elements, state machines, counters, and logic circuits work together to make elevator operations efficient, reliable, and safe. Through this presentation, we'll see how theoretical concepts of digital electronics are applied in real-world systems that we use every day. This case study connects digital electronics theory with the practical engineering. The main objective is to understand how sequential circuits are used in real-time control systems like elevators. In this system, we analyze the fundamental of sequential circuits, study state diagrams and timing diagrams, use flip-flops and counters for floor transactions, and design a basic elevator controller. So this project helps bridge the gap between classroom concepts and real industrial appliances. So we have the three main sequential circuits components used in elevator controls are flip-flops. This act as a memory element and store the current state of the elevator, such as which floor it is on. Then we have counters. This helps track the sequence of floors as an elevator moves up or down. The third one is state machines. This defines how the elevator behaves under different conditions like moving, stopping, or opening doors. Together, these components form the intelligence behind the elevator controller. Now let us see how elevator control system is divided. So elevator control system is divided into three sections. Input section. This includes floor, buttons, position sensors, door sensors, and load sensors. Then we have control unit. This is the brain of the system where sequential logic processes the inputs and decides what actions to take. The third one is output actuators. This controls the motor movement, door operations, floor indicators, and displays. This block diagram shows how user inputs are processed and converted into elevator actions. Now let us see where the sequential circuits are used and why it is used over here. So sequential circuits are different from combinational circuits because their output depends on the current inputs and the previous state. This means that the circuit has memory. This memory is essential in elevator system because the controller must remember the current floor, pending requests, movement directions. Clock synchronization ensures all changes happen in an organized way, making the system predictable and safe. Now let us see which type of flip-flops we have used and why I have selected this kind of flip-flops. In this design, we have used two types of flip-flops. JK flip-flop, it can toggle its output, making it useful in counters and state transactions. The second one is D flip-flop. It transfers input directly to the output on the clock edge, making it ideal for storing floor positions. These flip-flops help the elevator keep track of states and make correct decisions. Now let us study state diagram elevator FSM. The elevator controller is modeled as a finite state machine FSM. Each floor is represented as a state. S0 for ground floor, S1 for first floor, S2 for floor 2 and S3 for floor 3. When user presses a floor button, the system checks the request and moves to the next state. The state best design makes the control logic organized and easy to implement. So this is the state transition tables, which defines how elevator moves between the floors. For example, if the elevator is the first floor and receives an up request, it moves to the floor 2. If it is on the floor 3 and receives a down request, then it moves to floor 2. The controller uses this table to determine the next floor, motor direction, and the floor operation. This is the logical decision-making part of the elevator system. Now a very common question is that what if there is a multiple users? So the answer is over here. Then when multiple users request different floors, the system must decide which one to serve first. Obviously, the logic works look like this. The requests are stored in a queue. Then the elevator gives priority to the current direction. It continues upward request before changing the direction. This improves efficiency and reduces unnecessary movement. Now, to process signals efficiently, we have inputs and output circuits. We have encoders, which converts floor button inputs into binary values. Then we have decoders, which converts the controller output into motor actions like up, down, or stop. Priority encoders helps handle multiple simulational requests. This digital conversion simplifies the control logic. Now finally, let us see that which main algorithm is used over here. So the elevator control algorithm follows these steps. The first one is ideal state, which waits for user input. Then request detection, identifies floor request. Then movement logic, which moves the elevator to targeted floor. And then stop logic, stops and opens the door. This loop continues continuously, ensuring smoother operation. Now let us see how elevator uses priority logics. So the elevator uses directly priority logic. If moving up, it serves all upward requests before moving down. If moving down, it serves all downward requests before moving up. This avoids frequent direction changes and improves passenger efficiency. Now let us see how door is controlled. What is the sequence behind door control? So door control is the another sequential operation. Sequence is like opens the door, start timer, closes the door, and check for obstruction. If something blocks the door, it reopens automatically. This logic improves passenger safety. Timing diagram plays a vital role in every circuit. So for this, the timing diagram shows how output change with each pulse. At each clock cycles, the state updates, the motor signal changes, the door signal responds. This verifies that the elevator behaves in a synchronized and predictable manner. So finally, the complete circuit implementation. The complete circuit combines D flip-flops for memory, logic gates for decision making, and decoders for output control. All components operate together with the clock synchronization. This is the hardware realization of elevator controller. Here, the screen showcases the simulation results. Simulation confirms that flow requests trigger correct state transition, motor controls work properly, and door timing is correct. This validates that the sequential logic design functions as intended before real implementations. So now talking about the safety. Safety is critical in elevator system. The controller includes overloaded detection to stop operations if weight exceeds limit, emergency stop for manual override, then door sensor to prevent closing on obstruction, and fail-safe logic to move to a safe state during faults. This mechanism ensures reliable and safe operation. Now let us see their real-world applications. This design concept is used in multi-floor elevators, smart buildings, RT-based elevator monitoring, predictive maintenance systems. Modern elevator systems uses the same digital control principles at the larger scales. So this was about the application where finally or in the real time where we can implement this. Now let us see what are the key takeaways from all this explanation. The main lesson from this project are sequential logic provides memory and control. It states state machines manage flow transitions. Flip-flop stores the current state, and safety logic ensures reliability. This project demonstrates how digital electronics can solve the real-world automation problem. So, concluding this elevator control system shows how sequential circuit transform simple button inputs into intelligent real-time decision. By using flip-flop, counters, and state machines, the system achieves efficient movement, organized control, and passenger safety. What seems like simple elevator ride, it's actually the result of carefully designed digital logic working in perfect synchronization. This project highlights the importance of digital electronics in automation and proves that sequential circuits are the foundation of modern control system. So, concluding this, thank you.